So today I'm gonna be looking at. Well, I got this thing right here. This is my little. This is like my forearm strength thingy. All right. So I'm gonna be going at different distances from the point at which the mass is tied to, and see how that affects the time I can actually hold it. Obviously, I'm gonna try and go equal increments. You can see I already got marks on it. Like, you can't really see it. But I'm gonna keep the weight the same. I'm only gonna change the distance. I'm expecting the times to go down, but I'm wondering if that would be like an exponential curve or more of a linear curve. Obviously, I can fatigue after a few trials, so I'm hoping to do each distance only once and get actual good data from there. I'm gonna be recording on my stopwatch over there, and I'll link up the times hopefully. Okay, the first test I will be doing will be 3 inches from the point at which the mass is tied to the broomstick. I use the broomstick because I do have a plastic one. I have a plastic one right here, and this one is probably as close to like a weightless, rod, I guess we'd get to. But I didn't want to break it. I didn't want to bend it because that's no fun. So I'm actually using a wooden one. I just want to make that clear. So yeah, the first test will be 3 inches from the point at which it is tied. I got the timer right there. I'll do my best to, stop it or start it when I start and stop when I stop. The way I'm going at this is as long as I can keep it parallel. And I'm gonna do the lighter weights first. I'm gonna start off light with the 3. Then the second one's gonna be 6, then 9, then 12. So I'm actually gonna do 4, not 3. I'll start the time and we shut off. Don't look. Okay, and 3, 2, 1. All right, so I'm gonna, obviously that time's gonna be a little off. I'm gonna go by the time I dropped it. So it's probably like 109-ish. I tried to get 115, kind of tensed up there. So now using common sense is the amount of force because of torque. Because as they get further from the end, it's gonna increase. We're expecting the times to go down. Like I said, muscles can be weird. You need time to warm them up. But they're definitely warmed up now, so I'm not expecting any time close to probably 50 seconds after that one. Fully explain what I'm doing, so I want to see if there's any relationship, between the distance and then how much extra energy is required over a certain amount of time. I'm hoping that there is, because as I move further away, I'm gonna need more force, and I'm wondering if that force stays constant. You know what I mean? So if I find how much counter torque I need to apply to keep that thing parallel, and for as long as I do it, if that is somehow equal all the way across the board as I move further from the actual point where the mass is held, and my times will also decrease, it's kind of a, inversely proportional relationship. As one increases, the other decreases. Just from what I believe it will be, so I want to see if I could find a possible mathematical relationship between the two. Do 6 inches now, and I'll convert these all to meters, so my calculations are in metric. But and it's 15 pounds. I don't know if I mentioned that. I convert that to kilograms. So trial number 2 right now. like I said, that was not even close. So it's definitely, without looking in the mirror, it's hard to tell when I'm at parallel or not. So I kind of felt myself at the end, kind of relying on my bicep a little bit more, meaning I was kind of curling it, not really flexing my wrist. That's gonna be one of my errors, I'd say. 36, in terms of what I was expecting, that makes sense. I said it wasn't gonna be any close to what I got before. I don't even know. This 9 one's probably gonna be probably 12 seconds. So let's think about this. So I doubled the distance and my time almost exactly was half. So we got it. So let's think about if I triple it now from my initial one. So I was at 3, I'll be at 9 right now. Inches, I'll convert to meters. Time should be somewhere around 20, like 23-ish. So if that's right, we'll see. I'm gonna try to not look at the time for as long as possible to try and sway what I end up getting, because I want to do this as legit as I can. And if I go 4 times from the first one, then it'll be at like 15 seconds. So to be honest, I don't think I can hold that thing for 15 seconds. That was like a second and a half. So now I'm gonna do trial number 1 with the left. Okay, so we can see, I'll let you go by the time I dropped it, but we can see already we're pretty balanced as to which each side is going, so hopefully we can get a consistent trend in our graph. So now I'm gonna do trial number 2 on the left. Jeez. Again, really similar. I'm cramping now. We had a similar measurement. The 3rd trial for left. So, all right, I'm gonna try number 3 now. Like I said, hold on. We're expecting about 20 seconds. I'm gonna try not to look at it. I'll try to keep it parallel for as long as possible. In a perfect world, if we keep this trend going, we're looking at about 23 seconds. So let's see what we get. Yikes. I can definitely feel the effects on both arms of fatigue. You know, just losing energy. The trend's still kind of there, but jeez. This number 4 is gonna be like 2 seconds. All right, so we got trial number 4 now. Okay, so what you can probably assume is that my body is not a perfect system, and I do not have the same amount of energy at all times. I think if I did the heavier weights first, I could probably hold them a little bit longer. That would probably have an effect on the later weights. I'm not gonna do that again. Yeah, I'm curious to see how the forces and the times actually correlate, or no, how the times and the distance actually correlate. Obviously, you can assume that they're going to decrease the farther I go, but I just want to see if there's maybe a constant that exists between the two. All right, so just to show how I calculate all my data, so I had my hand as my axis of rotation. I wasn't going to include any of the other end of the broom behind me because that really had zero effect. Then I just changed my distances from the actual mass. The mass would come out to be 6.8 kilograms. You can see on the right side I have T2. That's my torque too, you could say. That's my force times my radius, first cross radius sine theta. And then seeing as my angle of my my mass to the rod was 90 degrees, so sine theta would drop out, sine theta turn to just 1, so it cancels out. The newtons of the object is actually 66.64 newtons, so I had to find myself, multiply that by my radius to find my newtons times meters. So basically my hand would have to apply a counter torque that would be equal in the opposite direction. As you can see by my arrows directing it. I'm a little force trigger of T2. I'm assuming I'm keeping my arm, or I'm keeping the weight perpendicular to my arms, so that there's no angular torques that I need to calculate. That would just be madness. So for trial 1, 3 inches translates to 0.6062 meters. Then trial 2, trial 3, trial 4, those are 3 inches, 9 inches, 12 inches. And then you can see all my times from holding my right arm to my left arm. They were pretty consistent the first two, and then I didn't think about this at all, but I write left-handed, so my left arm is like my left forearm, I should say, is more endurant to physical activity. I thought my throwing arm would be more strong. That's my right arm, because I'm throwing all the time. But I guess that would be more UCL, more shoulder activities, so that's not really helping me right here. So yeah, the only reason I think my left arm was that much better was, especially during round 3, that's 7 whole seconds of 66.64 newtons that distance as well. And then they finish out the same. So it's pretty interesting to see how just how this ended up working out. You can see obviously there's a similar trend. My times greatly decrease. I don't know if it's linear. I'll have to check in the graphs that I plug in about a second. But yeah, it should be interesting to see how the two correlate. Okay, so after plugging in my data for this lab, I'm actually really happy with the observations I made. So I've had this theory for, I'd say, a few months now, that the rate at which your muscles exert force, it doesn't decrease linearly, it decreases exponentially. And you can see by the curve fit of the graph, I know the data isn't exactly equal to one another, in that the times are a bit off, in terms of being the same for both arms, but either way, I'm really happy about this, because it just shows that the rate at which the body exerts force decreases exponentially. And even after I did this experiment, a few hours later I went back down there, and this time I did the heavier weights first, and I got 12 seconds, close to the what I predicted earlier in the video. And I was just like, wow, okay, I was right. Under perfect circumstances, like a rested body, you should be able to do this. So in a perfect system, it should be a linear graph, but seeing as the human body exerts energy in an exponential rate, the longer you go, the more force the more it's hard to get this. I'm just really happy that this is true. Let me just try and get my thoughts together for a second. And the reason I ended up doing the counter torque is because it's proportional, in that your sine of theta, it's 90, so it cancels out as 1. The distance is proportional to my actual torque. So if I were to take out counter torque and plug in my distance from the axis of rotation, those are linear. That's a proportional relationship. So it'd be the same looking graph, just with smaller numbers. Okay, to hopefully clarify any questions you still might have. So let's say this was my system. I put a mass on the end to see how the radius affected the time I could hold it. Now, it didn't, the times did not decrease linearly as my distance did. So automatically there was a relationship there. The exponential curve fit the best. So now it could have been, there was the quadratic one on there. That one looked all right. But I thought the exponential looked the best. So that leads me to believe that the rate at which the body exerts energy is an exponential curve. Seeing as it wasn't linear, as how I increase my distances linearly, there must be something else going on. Now, this could be muscle fatigue. This could be, how your body's feeling. It could be dehydration. I could have lost some energy, or not energy, some water during sweat. And all of a sudden, my body starts moving a little bit slower. It could be a million reasons, but from what I've gathered in this experiment today, my theory before any experimentation, that I don't know if I stated it in the video, but I know I had it. It was just floating around my head, and then this was like a great idea. Like, test if it works. That's true. And again, when I said I tested it with the heavier weights first, I got much greater times because my body hadn't used as much energy. Now, if I were to have done the light weights after doing the heavy weight, I can almost guarantee my times would have gone down. So I'm really happy that that's the way this went today.